I hope you're all having a great day. I am Mr. Ish. Thank you for joining me for this video. We are doing a comprehensive calculation which will involve Q, your reaction quotient, and KEQ, equilibrium expression and constants, all of that coming into play. It's a hypothetical question, but it has good learning value. We have this reaction at the very top, HBr, hydrogen bromide, everything here in gas, decomposing to give you hydrogen and bromine. You can see the initial quantities are here in moles, 0.4, 0.02, 0.06. The equilibrium constant is over there, 7 times 10 to the minus 2. You know there are no units. Everything is here being conducted in a closed environment with a volume 500 milliliters. You have to determine the Q, determine the reaction direction, and the equilibrium concentrations of these three items. Before we start, understand this. If Q is less than KEQ, your reaction will go towards the right in the forward direction. If Q is obviously greater than KEQ, your reaction will proceed in the reverse direction, generally towards the reactants. If Q is equal to KEQ, your reaction is at equilibrium. What is the difference between Q and what's the difference between KEQ? This right here represents the constant of a reaction which is at equilibrium. This here represents a constant of a reaction which is not at equilibrium, and that calculation could have been done at any time during that reaction except for when it was at equilibrium. If it was done at equilibrium, then you would be at this position where Q is equal to KEQ. Keep that in mind. How do you go about determining Q, which is our first question here? It's not hard. Understand the following item. You are looking at Q, which will be an expression made of those items. The products will always be on the top, and you can see these coefficients will serve as a exponent, and this right here is your Q and it's your equilibrium expression. But we have everything here in moles. I have a volume. To convert everything here into molarity, which is what you want to do, you want to do moles divided by volume. Each of those items here, which I'm just calling X, you would divide by 0.5 in liters. Milliliters converted to liters. 0.4 divided by 0.5, you know what that will be. This right here will become 0.8, and I'll put it for you right here. 0.02 divided by 0.5, because we have to convert these into molarities, this will become 0.04. 0.06 divided by 0.5, and you know this will become 0.12. All of these have units, molars. So we've done this conversion, and now these items we can run through here to determine their Q value. You'll do 0.12 times 0.04, these are their molarity values, divided by 0.8, but square, and determine what your Q is based on your scientific calculator. 0.12 times 0.04 divided by 0.8 square, I'm getting here 0.0075. What I'm getting over here is 7.5 times 10 to the minus 3, or 0.0075. I have a Kc value over here which is 0.07, and it's not a very small number, but it's not a very large number. Remember, I've told you in a previous video, your cutoff points are 10 to the 3 or 10 to the minus 3. Anything in between is kind of your gray area. This value 0.07 is falling right over here. Anyhow, keep that in mind. We have a value over here. Q is less than your Kc. 0.0075 is less than 0.07, so your reaction will go here in the forward direction, and you know that will be right. Your forward reaction is this. Hydrogen bromide will decompose, will continue to decompose to give rise to hydrogen and bromine gas until the reaction arrives at equilibrium. The essence of this quantitative factor and the fact that it is within this range will become apparent when we will do the equilibrium concentration determinations. How are you going to do this? Well, we'll bring a little table, initial, change, and end. For these three items you see, hence there will be three columns right here, as you can see. The initial is always now what we'll be using here with regards to molarity, because everything had to be converted from moles to molarity. You have 0.8, here you have 0.04, here you have 0.12. These coefficients, or the stoichiometry of the reaction, will come into play here in terms of the variables. This will decrease here by minus 2x, because 2 moles of these are giving rise to that in terms of the balanced equation. This will obviously increase by plus x, because coefficient here is 1, and here plus x. So this will be 0.12 plus x. Here will be 0.04 plus x. This will be 0.8 minus 2x. Now you have to write your equilibrium expression, and obviously we have this right here, this value. you'll have 0.12 plus x times 0.04 plus x divided by 0.8 minus 2x, but you're doing a square, is going to equal all of that right there, 0.07. Now we have work to do. You can't just eliminate these x's over here because you have a value here which is not too small. Therefore you have to do quadratic equation here, quadratic formula. All of that has to come into play. There's no shortcut now because that 0.07 is not too small of a value that you can just cross out these x's. When the numerator items are multiplied and this is opened up and taken on the other side, I've done the work over here on the side. The equation boils down to the following quadratic equation: 0.72 x squared plus 0.384x minus 0.04 equals 0. And now you have to run everything to the quadratic formula. Minus b plus minus square root b squared minus 4ac over 2a. Here's your a, here's your b, here's your c. And then you would actually solve for x because all of this is equal to x. And I've done this work as well. You can all confirm it on your own side. But when you solve it out, x here becomes equal to this. So with this value determined, what do we do with this? We put this here in places of x. That will give us our actual equilibrium concentrations of each of these three different species. And I'm going to run these values right here in places of x. Now I'll post the final amounts for you right here. It will be 0.8 minus 2 times that x value. Here we'll get 0.6215 molars. Everything here will be with regards to final concentrations. Here we get 0.1292. Over here it's going to be easy, 0.2092. You can see this started at 0.8, it has come down to 0.6215 as the reaction has proceeded. This has moved up in terms of concentration from 0.04 to this. Likewise, this has moved up. If you run these values here through your equilibrium expression, you should arrive at 0.07, keeping in mind that you have this square which will come through, but I'll run it for you and this will be our confidence builder. We'll do these divided by this square. As you know, the equilibrium expression would be that 0.2092 times 0.1292 divided by 0.6215 square. We're getting 0.0699, but you can round it up to 0.07, which is exactly this. So our entire procedure here is right. Again, I'll tell you, we ended up with a tedious quadratic equation and a formula that we had to use. We couldn't eliminate those x's and just do a simplification because this value is not too small. Only if it's extremely small can you eliminate those x's and make that calculation very easy. Here we had to actually do the quadratic formula approach and come up with this value right here. Plug it in to get your final equilibrium concentrations, which brings us now to the end of this video. Have a good day.